Yeah, thank you. I don't have questions concerning any theorems, but a physics question. So first of all, thank you very much for this very clear and, for me, eye-opening talk, which also has a bit of frustration for me. So in essence, you are solving or trying to solve the forward problem, right? You have some structure and you want to predict when it collapses under the influence of an earthquake. But actually, from an engineering viewpoint, what you really would like to solve is the inverse problem. You would like to get an answer to the question, what kind of building should I build that it's more resistant with respect to earthquakes? And on the basis of your talk, I get the feeling that answering or solving this inverse problem is close to impossible, or am I wrong?
So scientifically, I think it's very interesting, given a structure, what is the probability that it fails? Because this answers the question, what do we do with existing structures? Which is a very important question for earthquake engineering. Usually for new structures, what you do is you start accumulating safety factors. Okay, that's not really science, this is empiricism, but in the end you have something that is not really going to collapse. I mean, modern buildings wouldn't collapse under the earthquakes that we do expect. They're over-designed, I would say. The question is what happens with existing masonry buildings, all brittle reinforced concrete buildings, and so on. So it is interesting. Now, the inverse problem, I don't know whether it could be solved the way you suggest. I mean, like, when you design a structure, I think it's sort of like it has some degree of trial and error. So you're essentially solving the forward problem and see if it stands. This is I think the practice in the engineering practice. You have a method to solve the forward problem, and this is what you do. Maybe sometimes you overshoot. I don't know if this answers your question.
Yeah, thank you.
You're welcome.
Great. You know, I looked it up on internet, the theorem of Vassiliou-Buckingham. So there are two names.
Yeah.
So, okay, so it seems also to be called the theorem pi.
Yeah.
Say, just because I did not know the name until today, I'm very sorry, but I discovered that it's really fundamental. And so I'm very interested.
It is very interesting that usually they don't teach this theorem. And I find it very useful for dimensionality reduction of problems. Actually, I came across to this because my advisor was using it a lot, and he learned it from Professor Barenblatt, who moved to the US in 1991 from after the dissolution of the Soviet Union. Barenblatt was a student of Kolmogorov.
Okay.
And I see that many people working on physics do not know it. They have some fancy terms to perform dimensionality reduction, because, for example, this is a problem. This is a dimensionality reduction, a way to perform dimensionality reduction. Okay, I had 1, 2, 3, 4, 5, 6, 7 dimensions, and now I have 7 minus 3. I have 4 dimensions. And I was discussing with people, and they didn't even know that you can do this, and then start applying the statistical methods, because this, from here to here, it's exact. There is no approximation, and it is essentially no more than what we were taught in high school, that the units left and right should match.
And sorry, I'm asking for ignorance. Is there an explicit way to construct this function phi?
No, there is no explicit way. But the trick over here is that, say that you have to find this function f, and you need to do experiments. Okay, so you will need to do your test for different values of L, of this law, of rho, G, and so on. You understand that this grows exponentially. So Buckingham says that you can, instead of trying to find this f, your problem is defined by function phi, which has less arguments. So you need to do way less tests. And you can reduce the dimensionality by, I wouldn't say, it's not correct to say as many units as you have over here. It has to do with the rank of the dimension matrix. But often these two coincide, how many units you have in the rank of the dimension matrix. You see that all these are non-dimensional here. And this is a standard thing that people that have been doing structural testing have been applying. Oftentimes they don't really know that there is they call this a Buckingham theorem, because they just know by heart the artificial mass simulation rules, and they do this. But there is some theory behind this. There is a whole book by Barenblatt on this, and we have used it in other stuff. I mean, for example, for rocking structures, I would need to draw now to explain this. But it has a lot of, I mean, maybe the most well-known application was during the Cold War. The Americans had published a video of a nuclear explosion. So that was supposed, now the power, the energy was supposed to be something confidential. And the Soviets, by applying some dimensional analysis stuff, they figured out by how fast the wave was going, which they were able to tell from the video. They were able to figure out what was the energy of this explosion.
Yeah, this is really nice. Speaking of your, rocking structure, I did this was a perfect contact condition at just one point of, your structure with the soil.
Let me see. The support, yeah. I mean, if it is soil, you cannot really. So you're talking about the tests or the model?
No, the model.
The model.
The 1960 model, or I mean, I can't remember the exact.
The old one, the 62, the Housner one.
Yeah, exactly.
Yeah.
Yeah. So
he assumes that there is a point contact.
Okay, a point contact.
And he also assumes that when it impacts the ground, all the impact forces are concentrated here.
Ah.
Which, I mean, it didn't make a lot of sense to me, because I guess that when you hit, it's not that there's nothing going on here. I mean, there must be some forces here as well. But the only difference, if you assume a stress distribution here and do not assume all the impact forces concentrated here, the only difference is the value of the coefficient of restitution, the energy that you lose.
And then I find this very, very interesting, this structure. So in general, this is applicable also to any, if you have a soil, let's say, and you have some stone on the soil.
Yeah.
Could you apply such a rocking oscillator model? Or
so the initial attempts to study this oscillator, I think, were in the late 19th century by Milne in Japan. He was British, but he was in Japan at the time. And he was trying to back calculate what the acceleration of an earthquake was by observing overturned blocks, mainly in cemeteries. I think that was not the only one that was trying to back calculate PGAs based on such a block. The Greek seismic design code that hold it from 1959 to 1985 was derived by such observations. But the problem is that, as you can understand, this is a wrong observation, because if you assume that the acceleration that causes overturn is the one that uplifts it, you overestimate the peak ground. You underestimate the peak ground acceleration by a lot. because you need some acceleration to uplift this, which has to do with the slenderness. Actually, the acceleration that uplifts this is, if you do the math, is G tangent alpha.
Okay.
But then uplift is a different thing than overturning. If this block is very large,
yeah,
it needs way larger overturn, way larger acceleration, and most importantly, it needs this acceleration to persist so that it overturns. I mean, this guy is going to overturn when this corner, at least overturn statically, if this corner is right above this corner. Okay, so you understand that if I have a short duration impulse that manages to uplift this, but does not manage to bring this corner above this one, it's not going to overturn. And actually, the larger the block is, the harder it is to overturn it, because this distance that the distance that this corner has to run is much larger. This is why the Parthenon survives, because it's like 10. The columns are 10 meters tall, so this diameter here is, I think, 1.5 meters or something. So you need an earthquake that would have to enforce a 1.5 meter displacement, which is huge.
Okay. No, it's. I mean, I never came across this model, and it's really fascinating. Now, what happens if you have like a periodic chain of rocking oscillators? You know,
one next to the other.
Yeah, and you know, it's like you have a periodic unit cell. You know.
Okay, you're going to metamaterials. Okay.
Yeah. I mean,
frankly speaking, I've never thought of it. I mean, what I have studied like some 10 years ago is what happens if you have a column and another column next to it and another one, and on top, if you have a beam. Which would be a rocking frame, which would be the Parthenon. Okay. At least 2D. And a very interesting observation is it emerges directly from the differential equation that the frame is equivalent with a column that has the same slenderness alpha, yet larger size. So if the frame is equivalent to a column of larger size, then this means that the frame is more stable than the columns. Because we said that something larger is more stable than something smaller. So this means that I add weight on top in the form of a beam, and I increase its stability.
And the Parthenon, I mean, the fact that it's stable.
So this is counterintuitive, because usually top-heavy structures are easier to overturn, like an SUV overturns easily than a Formula One. But in rocking, this doesn't hold.
Okay, wow, this is really nice. Okay, but it's assuming this kind of point contact, ideal point contact, you know, condition plus the force all concentrated at, you have some...
Everything is rigid, yeah,
everything is rigid, and but it's I mean, this will be soon the 60th birthday of this anniversary of this paper. So it seems to be a really important paper. So it's hugely cited, or it's something which is...
It is hugely cited. Yeah, I think it is his most cited paper, and he's one of the most well-known earthquake engineering researchers.
I think Graham wants to intervene. Please do, Graham.
Oh, yes. I was sort of curious that you're looking at horizontal shaking. And I imagine, and probably that's what seismographs usually record, but I guess there must be a little component of vertical shaking. Is it valid to ignore that?
We just published this. Okay, so usually you do record vertical motion as well. Okay, now if you have a look, do I have the equation of motion anywhere? I have it here. Yeah, but I don't have the vertical component. Anyways, I mean, I can explain here maybe. When you take moments around this point, okay, you have some horizontal acceleration multiplied by this lever arm. The vertical acceleration multiplies by this lever arm, which is smaller, because usually you're talking about slender stuff. Otherwise, it would just slide. So this is like a physical hint why the vertical motion does not really influence. Now, the problem with rocking is that it is so sensitive that even the slightest change in everything would result into something very different. So the question is not whether taking into account the vertical component of an individual ground motion would change the result. Because if you're looking at individual ground motions, everything would change the result. Okay, even if I make this 1 centimeter taller. Okay, the question is, if I take 100 ground motions that are horizontal and 100 ground motions that have a vertical component as well, statistically, do these two different sets of ground motions create any statistically important difference? And the answer is that overall, no. The physical reason being that this lever arm is smaller than this one. Plus, overall, the vertical component of the ground motion is usually weaker than the horizontal. Plus, it is more high frequency. And frequency is very important in rocking because you need to have persistence. You need to be pushing for a long time.
That's interesting that it's a different frequency. You would have thought that the horizontal and vertical components would be coupled. And
different waves, P and S waves. Shear waves or
Oh, I see. Yeah.
Okay. PS, Raleigh, and all these are soil dynamics guys. I mean,
right.
I'm not sure I know all the details. Yeah.
Sure, I should have remembered that. Anyway, thanks for the great talk.
You're welcome. You're welcome.
Thanks a lot, Graham. You know, I'm looking at your paper, Probabilistic Validation of the Housner Rocking Model.
Yeah.
And okay, so you seem to have done some experiments. I can see some experiments that were done in ETH laboratory.
Yeah, I guess this is the conference paper, right?
Yeah. That's the 2017 Dean Conference, yeah.
Okay, the full thing is in ESD, in the Journal of Earthquake Engineering and Structural Dynamics, and it's called Is Rocking Motion Predictable?
Okay. No, that's really fascinating. Okay, so I mean, people, please do ask us some questions because I can see in the audience there are some people who are on the civil engineering side, and I mean, it's truly fantastic talk. I'm just like a kiddo. I'm learning so much that I'm getting really excited. Yeah, Bogdan, please ask a question.
Yes, Michalis, thank you very much for the talk. It was really very well presented, and I learned a lot of new things. And just wondering if you have thought about the response, the impact of the response of each column, if you have a periodic arrangement of these columns, the impact of the first one to the next one.
If they start hitting each other.
Yeah. I mean, the periodicity and if the response, the wave vector can be, I don't know, have some changes from the polarization, let's say vertical polarization to a different, to influence vertical movement to influence the relay waves, for example, the surface waves.
So
due to the periodicity of these columns.
Now, if you have a rocking frame like the Parthenon, they all move together. Yeah. So there is not such question. Where this question starts becoming important is, say that this is a nuclear waste container, and the nuclear industry wants to know how close they can put them so that they don't hit each other. And frankly speaking, I think nobody has studied this. Because for the elastic oscillator, if this was an elastic oscillator and this was another elastic oscillator, okay, and you want to know how close you can put them, I think there is the work by Derkuragian since many years, the square root of sum of squares, where you take the maximum response of the one oscillator, the maximum response of the other oscillator, you actually take the square, and then you take the sum, and then you take the square root to take into account the fact that these maxima will not happen together. Okay, because the obvious conservative approach is to assume that this will happen together. So you want the distance to be larger than absolute the maximum of the one plus absolute the maximum of the other one. For rocking, nobody has done it, and I don't know.
I think it will be an interesting study to see maybe which distance it's ideal to can influence the wave behavior. And
yes, it requires more probability than I'm comfortable with.
So speaking of which, obviously your probabilistic approach is one key ingredient in your ERC grant, isn't it?
Yes. Yes.
So can you tell us a bit more about this? You actually have some collaboration with statisticians or probabilists, or how does it...
Mainly this will generate, I guess, data. I hope. I'm confident that it will generate a lot of data that will be useful to people doing probability, like Sudre or Van Vatsikos or these people. But for the time being, I mean, we're overwhelmed with practical, lab stuff, totally experimental stuff. I mean, it's not easy to perform all these tests at such a small scale. It's not easy to create all the setups and everything. So there's not much probability going on yet. When it starts going on, I'm sure, I mean, I won't be able to do it by myself because probability is not my strong point. It never was since high school.
No, but which is, I mean, it's very interesting because you have a clear potential to interface your work with mathematical probabilists, and I mean, those kind of people, I'm sure, would get really excited by this kind of stuff.
Intuitively, I get the feeling what needs to be done. I mean, for example, like all these Kolmogorov, Smirnov tests and all this stuff, I didn't know them. I had to collaborate with Marco Brocardo, who was a student of the Curegian. And, intuition is one thing, but you also need to know the solid background, which I don't.
And again, yes, of course, Martin, please do. Yes, Martin.
Sorry, I didn't want to interrupt you, Sebastian.
No, of course.
I have a bit of a different question. What you said about chaos has slightly confused me. So to my understanding, the chaos that you have in the systems you talk about would be called deterministic chaos in physics. You agree with that?
I'm not sure how the term would be defined. I have discussed a bit with some friends of mine from applied math, and they exactly told me this, that chaos, there is a solid definition for chaos for this kind of problems. You have your ODE or PDE or whatever, and you have your initial values and you try to predict the response. There you can discuss about chaos. Deterministic, or I don't know how else it could be called. I asked them, is there any mathematical background to discuss about whether I can predict a CDF? Can I discuss about mathematically how will I be able to decide whether this is a chaotic or not problem? They told me there are no tools. So mathematically, there's no discussion about this.
I'm a little surprised that they say that, because there are tools in the textbooks of deterministic chaos that you can look for some embedding Hausdorff dimension of the reaction of your system and actually classify that even.
How are they? Where should I look at?
Well, if you look at the attractor of the governing equation, and you look for the Hausdorff dimension of that attractor, you can distinguish deterministic chaos from random processes. Just for example, there are whole books I have in my shelf on deterministic chaos. But actually what I wanted to say is something different. That the same problem is faced by people working on climate predictions.
Exactly. This is what I told them.
For which the Nobel Prize in physics last year was actually given. So they have somehow learned to cope with this sensitivity on the initial conditions and still make some solid predictions of systems that are deterministically speaking chaotic. So can you learn something from these communities?
I mean, absolutely. I think I should learn from them. Frankly speaking, I haven't really done it yet, but the climate thing is exactly what I had in mind. I mean, because it's a different thing to predict what the weather is going to be like in a couple of days, and often meteorologists are very off for this. But and the different problem to predict the mean temperature after, I don't know, 5 years. So I guess these are two totally different stuff. So like when you average, stuff smoothen out. This is what I intuitively understand. So this is what you're doing here. You're taking the median response. So you expect that this is more smooth, yet hence more predictable. Or like, you know, when you're watching a football game, okay, if you try to predict the trajectory of the ball, there is no way you're going to find it. But if you try to predict if Juventus is playing against a crappy team who's going to win, you know that Juventus is going to win. So this is how I was thinking, and I thought that this is a different problem that we're studying here, and we're stuck with this problem because they were only able to test for one ground motion. Understandably, they have a specimen that breaks. They cannot do this. Now, if there is any other mathematical background that I would be able to use here, if I try to propagate the uncertainty, okay, like somebody might say, okay, I mean, I can assign a PDF at the material properties and then try to see how the uncertainty propagates forward. And then this would give me some bounds or some PDF of the response that I would be expecting. This is the standard thing that they do in people that are dealing with uncertainty quantification in earthquake engineering. The problem, I see two problems with this approach. The first is that in the end, I would like to have some tests, okay, to validate what they're saying, but this is not feasible, okay. And the other problem is that our problem in earthquake engineering is more fundamental. It's not that we do not agree on the PDF of some parameter. We do not agree on the model. Now, what I hear that people do is that they take a bunch of models and then they take the average, or they put some weighting functions. Yeah, but this now starts not being so much science. I mean, if I just take whatever model is on the market and I take the average without being able to validate in the end, this is like, you know, voting for what is right or wrong in science. I don't have any other suggestion than voting. Okay, but this is not science. I don't have anything better to suggest. But I also understand that this has a large, I wouldn't say probability, because it's a large chance of being very off. Not the least because, you know, you have a model, you have 50 students, and these 50 students have variations of this model. Or you simply might be wrong. Even, I mean, if you see the blind prediction contest, some of the people that did very bad are very well-reputed researchers. I was tempted, like, to try to create a weighted average based on, I don't know, how many papers, how many citations. But then I thought, come on, what am I doing? This is ridiculous. But for sure, I mean, like, this is the blind prediction contest is an example of this. That you cannot weight, you cannot, like, take average. All these people are the enfant gâté of the avant-garde of earthquake engineering, and they see how off they were. Yeah, I mean, I've been in talks where one of the contestants was in the audience. They didn't really like it. I mean, I need to find better words to say this, but, you know, I'm not saying that I would be doing better. This is as much as we know.
No, I understand, and I appreciate your response, and I have no solution myself. I'm just thinking, once again, of climate research, where they also predict, say, the global temperature in 100 years. And they are, like you, unable to do experiments, or actually you can do an experiment, but you have to wait for 100 years to get the answer to this. but still people have somehow gotten the Nobel Prize for these kind of things. And I'm kind of hoping that they have done something more solid than averaging over 100 different models.
I've seen important reports where they just average 100 different models, especially for climate change. Imagine
average.
Shut up.
I mean, what kind of averaging? I mean, some kind of stupid averaging. I mean, just, you know.
It was a report that was just, I mean, I don't remember the details, but they were just giving maybe bounds between different models. But I mean, I guess if you try to average what Galileo was saying with other people of his time, I mean, one is wrong and one is right. In the end, again, I mean, that goes way beyond the talk. In the end, yes, we are going to be doing averaging. There is no other solution. If scientists disagree, what do? You average. Okay, but in 10 years, this average might be very different.
Mm-hmm. Okay, do we have any more questions? I mean, it's a good opportunity for people in the audience to come forward with any questions they have in mind. So I know that, I mean, I'm kind of obsessed by this, but to me, you know, on your right panel, I can see some kind of metamaterial, some kind of periodicities.
Okay.
So I would imagine that you can suppress the longitudinal compressional vibrations. You can find a stop band in this, or, you know.
I'm not sure I got it. The suppress what?
In fact, since you have some periodicity in the vertical direction, you might.
You're talking about what I'm sharing now? Or?
Yeah.
Okay.
Have you studied these kinds of things? Try
to study this as a metamaterial.
Yeah.
I don't know whether anybody has studied. So every building essentially is a metamaterial. If you have a typical floor and you have a 20-story building, yeah. I mean, I don't know if somebody has studied it. I haven't.
So essentially, with your shaking table, I mean, you essentially look at the transverse vibration.
Yes.
It's kind of.
This is the most important. Yeah.
This is the most important. Okay.
Yeah.
Right.
Yeah.
Okay. So if no one else asks. Bogdan, perhaps you have one more question, of course. Bogdan?
I was just wanted to say that we have platforms that you can also have vertical tests, vertical simulation, and and maybe both in the same time.
They're usually a bit more expensive. I mean,
yeah.
And what kind of frequency for this shaking table? What is the typical frequency?
So in the prototype scale, an earthquake would have dominant frequencies. So I think in terms of periods, the periods would be between 0.5 seconds and maybe 1 second, 1.5 seconds. So if you go at a prototype at a model scale of 1 to 4, these periods would be 1/2 of this.
Okay, this is very exciting stuff, and I would like to thank you again for you.
I thank you a lot for the invitation.
I mean, it's a great pleasure to reach out to people like you. Okay, so perhaps Bogdan, you could say a couple of words on our next speaker, webinar speaker, next Tuesday.